I want you to picture something for a second. Imagine you're walking through, say, a massive manufacturing plant.
Oh, yeah. Like maybe a heavy-duty pulp and paper mill?
Yeah, exactly.
Yeah.
Or even a sprawling power generation facility.
Mm.
And the sheer scale of it is just, well, it's overwhelming.
Right. The noise alone is incredible.
Exactly. The air is thick, the humidity is completely off the charts, and you can feel the vibration of the floor traveling right up through your boots.
If everything around you is just built for absolute heavy-duty punishment.
Right. You're walking past these huge vats, massive gearboxes, and sprawling petrochemical storage tanks. And you look at these colossal machines, and you naturally think, well, they're practically invincible.
I mean, they certainly look invincible.
But the truth is, the life or death of these multi-million-dollar metal giants actually comes down to a tiny, incredibly sensitive device that's protecting them from an invisible enemy.
Which is such a wild contrast if you really think about it.
It really is. So welcome to today's deep dive. Our mission today is to figure out how these massive machines rely on highly engineered, essentially lungs, to survive their own environments.
We're specifically looking at the tech sheet for DES-CASE HydroGuard Series breathers.
And it is a phenomenal piece of engineering to unpack.
Yeah.
We tend to focus on the massive physical forces in industrial environments. You know, the horsepower, the torque, the immense weight of the equipment.
Right, the stuff you can easily see and feel.
Exactly. But the real day-to-day threats that actually take these machines offline, they are often microscopic. Dirt, airborne moisture.
The silent killers of heavy industry.
Yeah, precisely.
Yeah.
And what's fascinating here is that what makes studying this specific piece of equipment so compelling isn't just the raw operational data. It's the broader story it tells about preventative maintenance in what engineers call steady-state operations.
Steady-state operations, so just normal, everyday running.
Exactly. It's an entire philosophy of mechanical preservation all packed into this relatively small plastic cylinder. Okay, let's unpack this, because before we look at the solution, we really need to understand the problem. Why does a sealed storage tank or a heavy-duty transformer even need to, quote-unquote, breathe in the first place?
That's the big question, isn't it?
Right.
Right.
Because if the outside environment is so hostile, like you said, with the dirt and the moisture, you'd think the golden rule would be to just seal the tank shut, weld it, and never let the outside air touch the inside.
Yeah, that is a very common assumption. I mean, it makes intuitive sense.
Keep the bad stuff out.
Right. But physics simply won't allow a completely sealed system in these applications.
Wait, really? Why not?
Well, machinery just isn't static. Even in a steady-state operation where a machine is humming along, doing its normal job, you have significant temperature fluctuations.
Oh, sure. Like from the friction of the gears.
That, or even just the weather. Imagine a massive outdoor storage tank.
Oh, yeah.
As it heats up under the afternoon sun, or as a gearbox heats up during intense operation, the air and the lubricating fluids inside that casing expand.
Okay, basic thermal expansion.
Exactly. And as the sun goes down and it cools off, those fluids and gases contract. This thermal expansion and contraction causes the system to essentially exhale and inhale.
Wow.
Yeah, and if it couldn't breathe, if it was totally sealed, the pressure buildup would eventually blow the seals right out.
Ah, so it really is literal breathing. It's expanding and contracting, almost like a chest cavity.
Literally. And then, beyond just the temperature swings, there's the issue of fluid displacement.
Which means what, exactly?
So, say a hydraulic pump activates and suddenly pulls 50 gallons of oil out of a reservoir to move a giant mechanical arm.
Okay.
Well, something has to take up that empty space inside the tank immediately. Nature abhors a vacuum.
So the system aggressively inhales ambient air just to equalize the internal pressure.
Precisely.
But in the target environments we're talking about, I mean, the tech sheet specifically lists pulp and paper mills, washdown areas, high humidity zones. That ambient air is an absolute nightmare for internal machinery, right?
It's the worst possible thing for it.
Because if a tank inhales water vapor from a high humidity room, that water is going to mix directly with the internal lubricants.
Which is catastrophic. Water degrades industrial fluids incredibly rapidly.
It breaks down the oil.
It causes oxidation and corrosion of the metal components. It ruins the fundamental lubricating properties of the oil. And it can even encourage microbial growth in certain fluids.
Microbial growth, like mold growing in your gear oil.
Yeah, exactly. It's a huge issue. And alongside the water vapor, that ambient air is carrying microscopic particulate matter. Dirt, dust, soot, ash,
just floating around in the factory air.
Right, and if those particles get into a high-speed, high-pressure gearbox, they act like liquid sandpaper.
Oh, man. Liquid sandpaper. That paints a picture.
Yeah, they get between the microscopic tolerances of the gear teeth, scoring the metal. That creates metal shavings, which then leads to this cascading, catastrophic failure of the whole machine.
Which brings us to the first line of defense listed on the HydroGuard specs. To stop that liquid sandpaper, they boast a filter efficiency of 3 microns absolute.
Yes, the 3-micron filter.
Now, to put that in perspective for you, the listener, a single human hair is roughly 70 microns thick.
Right.
And a single red blood cell is about 8 microns. So a 3-micron filter is like this ultra-strict microscopic net. It catches particles drastically smaller than a single cell, ensuring that only the absolute purest air can even get near the machinery.
And we should definitely clarify the terminology there, because the use of the word absolute in that filtration spec, that's a crucial engineering distinction.
Okay, how so? What's the alternative?
Well, in industrial filtration, you often see nominal ratings, which basically means the filter catches, say, 50 or 60% of particles at that size.
So it's more of an average.
Exactly. It's a suggestion almost. A 3-micron absolute filter, on the other hand, means it stops virtually everything 3 microns or larger, period.
No exceptions.
Right. Usually around 99.9% efficiency. It is a hard physical barrier. But, stopping the dirt is only half the battle.
Because of the moisture.
Yeah. You still have to deal with the water vapor, the actual humidity in the air that is passing right through that physical filter.
And here's where it gets really interesting, because this device doesn't just leave a hole open to the air with a nice filter over it. The tech sheet details the exact mechanics of how this breathing is controlled.
Yes, the check valves.
Right. The HydroGuard features a check valve with a cracking pressure of 0.1 psi, or 0.007 bar for our metric listeners.
And that specific, incredibly low number is deeply deliberate.
I was looking at that 0.1 psi and thinking about it like a highly sensitive, incredibly exclusive bouncer at a club door.
Okay, I like that.
Right. So the club is the internal reservoir of the machinery, and the bouncer keeps the door firmly shut against the harsh, dirty outside world. He doesn't let any air in or out.
Total lockdown.
But the moment the internal pressure of the tank changes by exactly 0.1 psi, just the tiniest, most perfect little nudge indicating that the machine actually needs to equalize, the bouncer opens the door, allows the system to breathe, and then immediately shuts it again.
That is actually an incredibly apt analogy, because the primary job of that bouncer is isolation.
Keeping the inside separate from the outside.
Right. That cracking pressure isolates the internal system from ambient environmental fluctuations. So if a strong wind blows across the top of the tank,
it stays closed.
Exactly.
Right.
Or if there's a minor barometric pressure drop from a passing thunderstorm, the breather just ignores it and remains sealed.
So it's not just constantly breathing in and out with the weather.
No, and that extends the life of the breather incredibly, because it's not constantly processing humid air unnecessarily. It forces the system to only breathe when the machine itself dictates it.
Okay, that makes a lot of sense.
But when that check valve does open, the air passes through the second major defense mechanism, which is the hydrophilic media.
A silica gel.
Right. And this relies on the chemical process of adsorption.
With a D, right. Adsorption.
That's adsorption. It pulls the water vapor out of the incoming air and traps it on the massive internal surface area of the porous silica beads.
And it does that without turning into a liquid or anything, right?
Exactly. It does this without actually changing the physical state of the gel itself. It's essentially stripping the humidity completely out of the air before it ever touches the oil.
And the brilliant part of that design, I think, is the color indication. The sheet highlights that the silica gel shifts from blue to pink as it reaches its maximum water retention.
The visual indicator is huge.
It is, because if you picture the environment we talked about at the top of the show, a massive, loud, complex petrochemical facility, the lighting is probably poor, things are messy, and you certainly don't have time to unscrew a complex filter housing and run a lab test just to see if it's full of water.
Oh, absolutely not. Maintenance teams do not have time for that.
Having a simple, immediate visual cue like blue means it's working, bright pink means it's time to change it, that has to be an absolute lifesaver for maintenance technicians walking the floor.
It really is the essence of effective preventative maintenance.
Just keep it simple.
Right. Good engineering takes a highly complex chemical process, like the absorption capacity of a desiccant under varying atmospheric conditions, and just turns it into a binary visual signal.
Blue is good, pink is bad.
Exactly. You don't need a diagnostic computer or some fragile moisture sensor. You just need your eyes.
Okay, so the inside is this highly delicate, perfectly calibrated environment. We know how these lungs work. They have the strict 3-micron net, the 0.1 psi bouncer, and the blue to pink water-absorbing gel.
Right, the core technology.
But the tech sheet mentions two main models. You've got the miniature DCHG1 and the standard DCHG8.
Yes.
And I'm looking at the diagrams of these things in the document, but it's hard to get a true sense of scale from a piece of paper. Just how different are we talking between the miniature and the standard?
It's actually a pretty significant jump because scale is everything in industrial applications. The miniature HG1 is quite compact.
How compact?
It's about 7.2 inches tall and 2.5 inches wide, and it uses a 38-inch multi-fit thread to attach to the machine.
Okay, so relatively small.
Yeah. Inside, it holds 127 grams of desiccant, which is about 0.3 pounds. That gives it a maximum water retention capacity of 50 milliliters, or roughly 1.7 fluid ounces.
All right.
And the specs note that its max airflow when the pressure drops by 1 psi is 1 cubic foot per minute, or 40 liters per minute.
And the standard model, the HG8.
The standard is much larger. It's nearly 10 inches tall and over 4 inches wide, and it uses a larger 1-inch multi-fit thread.
So it's beefier.
Much beefier. It holds nearly 3 times of the desiccant, 365 grams, or 0.8 pounds, which pushes its water capacity to 144 milliliters, or about 5 fluid ounces.
Okay, big jump to capacity.
And crucially, its max airflow at that same 1 psi pressure drop leaps all the way up to 14 cubic feet per minute, nearly 400 liters per minute.
Wow. Okay, so what does this all mean?
In what sense?
Well, if I'm walking the factory floor as a maintenance engineer, and I look at the side of a gearbox and see that its total volume is, say, 45 gallons, I just grab that miniature HG1, right? Because the spec sheet clearly says the miniature fits, quote, up to 50-gallon gearboxes or storage tanks. So I just match the volume to the tank, and problem solved.
You would think so. It seems incredibly straightforward, right?
Yeah, 45 is less than 50.
But doing that could actually destroy your machine.
Wait, really? Just going by the gallons?
Yes. Let's look at engineering note number 2 in this document.
Okay.
It explicitly warns that sizing is not just a volume matching game. The volume of the tank is just one variable in a highly complex equation.
So what else matters?
Well, sizing must account for ambient humidity levels, the frequency of airflow, operating temperatures, and most critically, the fluid displacement rates.
Ah, okay. The fluid displacement rate, that's the speed at which the oil is being pumped in or out of the tank, right?
Exactly. How fast the fluid is moving.
Because the specs say the standard HG8 can handle a maximum reservoir fluid flow of 105 gallons per minute, whereas the miniature HG1 can only handle 11 gallons per minute.
Precisely. And this is where the flow rate graphs provided in the document become essential for an engineer.
The graphs with the straight lines.
Yes. The graphs show a linear relationship between the flow rate of the air and the pressure drop across the breather, which is represented as delta P.
Delta P. Okay, so meaning the faster the air tries to rush through the breather's filters and valves, the more physical resistance it meets.
Exactly. Think about the physics of it. Let's say you put a miniature HG1 on a hydraulic system.
Right.
The tank might only be 40 gallons, so you think the miniature is fine based on volume.
Makes sense.
But suddenly, the machine activates and displaces 30 gallons of fluid in a single minute. The system instantly needs to inhale 30 gallons of air to replace that volume and equalize the pressure.
Oh, I see.
The tiny HG1 simply cannot flow air fast enough through its small valves and dense silica bed to keep up.
So the 0.1 psi bouncer at the door just gets completely overrun.
The bouncer gets trampled,
Yeah.
and the door itself isn't wide enough for the crowd. The system starves for air.
Wow.
If you look at the flow rate graph for the miniature model, trying to force even 4.5 cubic feet of air per minute through it pushes the pressure drop up to nearly 1.8 psi.
And what happens to the machine when that pressure drop gets too high? When it's struggling to breathe?
It creates a massive vacuum inside the reservoir headspace, and that vacuum puts immense destructive mechanical stress on the machinery.
Like it's choking.
Exactly. The pump is trying to pull oil, but it's fighting a vacuum. This can cause the pump to cavitate.
Cavitate? What's that?
It means the pressure drops so low that the oil actually boils at room temperature.
Wait, boils just from low pressure?
Yes. It creates these vapor bubbles that violently implode and destroy the metal pump impellers. Or the vacuum becomes so strong that it literally sucks the rubber seals of the machine inward, causing catastrophic oil leaks.
Okay, that makes perfect sense. You can't just slap a tiny lung on a machine that sprints, even if the machine itself has a small chest.
That is a great way to put it.
You have to size the lung for how hard the machine is breathing, not just its total volume.
That is a perfect way to synthesize it. You size for the dynamic state, not the static state.
Right.
And, that engineering note also mentions chemical compatibility, which bridges us perfectly to the next reality of these devices.
Right, because so far we've talked entirely about the inner workings protecting the oil from the outside air.
Right.
But this thing is sitting directly on top of a gearbox in a 200-degree diesel fume-filled room. How does the plastic casing of the breather itself not just melt or dissolve in that kind of extreme environment?
It really comes down to some serious material science. The tech sheet specifies a safe operating temperature range of -20 degrees Fahrenheit all the way up to 200 degrees Fahrenheit.
Wow.
That's -29 Celsius to 93 Celsius. Operating seamlessly across a 220-degree swing without the plastics warping, becoming brittle, or the valves failing, that is no small feat.
Yeah, looking at the materials list, it reads like the recipe for high-tech riot gear.
It really does.
The main housing uses nylon 66, that is 30% glass-filled, alongside polycarbonate, polypropylene, and silicone. The filters themselves are polyester and polyurethane. I'm assuming that glass-filled nylon is acting like a literal suit of armor for the delicate silica gel inside.
Absolutely. Adding glass fibers to the nylon polymer matrix drastically increases its tensile strength and its thermal stability.
So it holds its shape.
It prevents the polymer chains from sliding past each other when they get hot, which means the plastic housing won't warp or deform under high heat.
And if it did warp?
If the housing warped even a fraction of a millimeter, it would compromise the airtight seal, and those sensitive 0.1 psi check valves would be rendered totally useless.
But the threat isn't just the heat from the room, right? Because the breather is screwed directly into the top of the oil reservoir. It is constantly exposed to whatever is sloshing around inside the machine.
Right, and this raises an important question about chemical compatibility. The breather is inhaling and exhaling the fumes of the industrial chemicals it sits on.
Oh, right, the vapors.
It's not just liquid oil splashing up. It's vaporized synthetic hydrocarbons interacting with the polymers of the breather 24/7.
That sounds highly corrosive.
It is. The tech sheet states the breathers are chemically compatible with all mineral oils, most synthetic oils, and diesel fuels. They're also REACH compliant. The device basically can't be allowed to dissolve itself from the inside out just because it's breathing hot synthetic oil vapor all day.
And that actually brings up a subtle but really fascinating difference in the spec sheet between the miniature and the standard models.
Yeah.
The seals.
Ah, yes. The O-rings.
Yeah, the miniature DCHG1 uses both Buna N and EPDM seals, but the standard DCHG8 only uses Buna N. Why the difference? I mean, seals just rubber rings?
They are definitely not just rubber rings, and mixing them up is a recipe for disaster.
Really?
Oh yeah, the mechanism of chemical compatibility is incredibly specific. Buna N, which is also known as nitrile rubber, is fantastic at resisting petroleum-based oils and diesel fuels. It holds its shape perfectly in those environments.
Okay, so standard oil is fine with Buna N.
Right. But EPDM rubber is fundamentally different. EPDM is designed to resist specific synthetic lubricants, things like phosphate esters, which are heavily used in fire-resistant aviation or industrial hydraulic fluids.
So what happens if you use an EPDM seal on a standard petroleum tank by mistake?
Well, if you take an EPDM seal and expose it to standard petroleum vapor, the chemical structures are actually too similar.
Too similar.
Yeah, the EPDM rubber essentially tries to dissolve into the oil. It absorbs the petroleum, swells up like a sponge, loses all its structural integrity, and eventually just turns to mush.
Wow.
Your airtight seal is completely gone. So the fact that the miniature HG1 offers both seal types suggests it is targeted for highly specialized, smaller batch chemical or advanced hydraulic setups where you might see those exotic synthetics.
That makes sense.
Whereas the standard HG8, relying only on Buna N, is built primarily for massive bulk petroleum storage.
It is amazing how much engineering, from the fluid dynamics we talked about to this polymer chemistry, is packed into something so deceptively simple.
It really is a marvel.
We started this deep dive talking about massive, multi-million-dollar metal giants and deafeningly loud manufacturing plants. And it turns out the ultimate bodyguard for all that equipment is just a compact plastic cylinder filled with color-changing gel.
armed with a 3-micron absolute filter, a zero point 0.1 PSI check valve, and a glass-filled nylon chassis.
Exactly. So the next time you, our listener, are driving past a sprawling power plant or a heavy manufacturing facility, and you see all those massive structural gears and towering storage tanks, you'll know the secret.
You'll know what's really keeping them alive.
You'll know about the tiny blue-to-pink sentinels standing guard on top of them, quietly filtering the air, fighting off microscopic enemies, and keeping the massive gears turning safely.
It really is a masterclass in isolating a complex system from its chaotic environment to ensure its long-term survival.
It absolutely is.
And, looking at all this technical effort leaves me with a final, somewhat philosophical thread to pull on.
Oh, let's hear it.
We've spent this whole time discussing the immense engineering, the precise filtration, and the absolute strict pressure control required just to keep a robust machine functioning at a steady state.
Right. Just to keep it normal.
Exactly. It takes an unbelievable amount of unseen energy to maintain that baseline. It makes you wonder, how much unseen energy, mental filtration, and pressure regulation are we constantly expending in our own lives just to maintain our own personal steady state against the chaotic environments we navigate every day?
Man, I love that perspective. It really does take a lot of work just to keep humming along normally. Maybe we all need a little blue to pink indicator to tell us when our own capacity is maxed out.
Wouldn't that be nice?
But until someone engineers that for us, we'll just have to remember that surviving the most overwhelming, heavy-duty environments isn't always about having the thickest armor. Sometimes it's just about having the smartest lungs.